Lesson 10-5 Perfect Squares and Factoring. And in this lesson, you learn to identify and factor perfect square trinomials. And it's important because you can use factoring to solve problems involving finance and construction. Let's take a look at this number theory integration. Recall that the numbers 1, 4, 9, 16, and 25 are called perfect square numbers since they can be expressed as a square of an integer. Okay, so 1 is a perfect square because if I get 1 times 1, okay, 1 times 1, what it means is that, okay, the dimensions of my square will be equal to 1. That's why the area is 1. And same thing with 4. Uh, 4 is a square number again because again, if I get another square like this one, and the area of my square is 4, dimensions are 2 and 2. So 4 is a perfect square, 1 is a perfect square. That's the same thing with 9. It's a perfect square because 3 times 3 is 9. 4, 16 is a perfect square because 4 times 4 is 16. And 25, as you see here, is a perfect square because the dimension of the square is equal to, dimensions of the square is equal to 5. Okay, so they can all be expressed as a square of an integer. So the equation 5 squared is equal to 25 can be modeled as the area of the square having the side length, the side having a side of length 5 as shown at the right. Okay, so knowing this, okay, we can now move on to binomials. Suppose 3 plus 2 is substituted for 5. Then 3 plus 2 squared can be modeled by using a 5 by 5 square and divided it into 4 regions as shown at the right. So let's just substitute 5 with 3 plus 2, which is a true statement. So that means we can model 3 plus 2 using the same model right there. It's a square, but we've divided it into 3 squared into 4 areas now. It's still the same square. Okay. The sum of the areas of the 4 region equals the area of the square. So what we do is this. Okay, so we have 3 squared. 3 plus 2 squared is equal to 3 squared. Okay, using the Punnett square method. 3 plus 2 squared. Sorry, 3 squared plus 2 times 3. Okay, y right here. And 3 times 2, which is right there, plus 2 squared. So everything in that square we just simply added here. Or it's the same as 3 times 2 plus 3 times 2 plus 2 squared. And we can simplify this to become 3 squared plus 2 times 3 times 2 plus 2 squared. And if you notice, okay, the last line shows a very interesting relationship when you talk about binomials. Okay, now look at this one. Okay, this is the relationship. So we have quantity 3 plus 2 squared is equal to 3 squared plus 2 times the quantity 3 plus 2 plus 2 squared. And if you notice, okay, the first term and the last term are both squares, and the middle term is twice the product of 3 and 2. Okay, so using this particular model, okay, the square of this binomial is the sum of, so the square of this binomial is the sum of the square of the first term, okay, twice the product of the first and the second term, and finally the square of the second term. Okay, so which brings us, okay, to that if we look at the if we substitute 3 and 2 to a and b, okay, we can actually say that this observation is generalized by the model at the right, something like this, where now you have, instead of 3 and 2, we substitute with simply variables to generalize it. So you have a plus b times a plus b will give us a squared. times AB times AB again times B squared. So A plus B, the quantity A plus B squared, is equal to A squared plus 2AB plus B squared. Okay? To square now A times negative B. Okay? Write the binomial as A plus negative B, then square this binomial. So we have A times the quantity A times A minus B squared is the same as the quantity A plus negative B close quantity squared. Okay, or A squared plus 2 times A times negative B plus negative B squared, or A squared minus 2AB plus B squared. So look at the difference between the two. Very minor difference. Okay, in squaring the quantity A plus B, okay, all signs are positive. In squaring A minus B, okay, the first sign is negative, the second sign is positive, which brings us to a rule on perfect squares, trinomials. We call these perfect square trinomials because obviously they form a perfect square. Perfect square trinomial simply state that if you have the quantity A plus B squared, it is the same as A squared plus 2AB plus B squared. And the quantity A minus B squared is the same as A squared minus 2AB plus B squared. Remember, we did this at the end of chapter 9. We call this in our special products the square of a sum and the square of a difference. Okay, in factoring method we call this now perfect square trinomials. Okay, so this is now your perfect square trinomials, and these patterns can be used to factor trinomials. So basically we can simply use this pattern to factor certain trinomials. Okay, and let's see how we can use this. So before that, let's take a look at this model. Okay, you have v plus 3 and v plus 3. That's a perfect square. That's a square because the dimensions are the same. So if we model this is v squared, 3v right over here, another 3v, and this is 3 squared. And then squaring a binomial simply means v squared plus 2 times v3, okay, plus 3 squared, or v squared plus 6v plus 9. So if you're factoring a perfect square trinomial, we simply do the opposite. V squared plus 6v plus 9 is equal to the quantity v plus 3 squared. Okay, another example, this model right here. Again, this forms a square because the dimensions are the same. Okay, so we have now the quantity 3p minus 2q squared is equal to adding all of these monomials up, you end up with 9p squared minus 12pq plus 4q squared. And if you want to factor this trinomial, get the factors, we simply do the opposite. 9p squared minus 12pq plus 4q squared is the same as the quantity 3p minus 2q squared. Okay, so these are perfect square trinomials. And to determine whether a trinomial can be factored using patterns like this, you must decide if it is a perfect square trinomial. In other words, you must determine if it can be written in the form of a squared plus 2ab plus b squared, or in the form of a squared minus 2ab plus b squared. So for a trinomial to be one of these forms, the following must be satisfied, and there are 3 things that you need to ask yourself for it to be a perfect square. Oh, why is that 4? There are 3 things that you need to ask yourself for it to be a perfect square trinomial. Okay, first question you need to ask yourself, okay, is the first term a perfect square? Second thing, okay, is the third term a perfect square? And the third question you need to ask yourself is the middle term either 2 or negative 2 times the product of the square root of the first term and the square root of the last term. Okay, And let's see how these three questions come into play. Determine whether each trinomial is a perfect square. Trinomial, if so, factor it. So you have 4y squared plus 36yz plus 81z squared. Okay, so again, to determine whether 4y squared minus 36yz plus 81z squared is a perfect square trinomial, we need to answer the three questions. Is the first term a perfect square? Okay, and to answer that question, before we go to the next question, so 4y squared, is it 2y squared? The answer is yes. Is the last term a perfect square? 81z squared. Okay, is the same as 9z squared, so the answer to that question is yes. Okay, and if you notice, this is our a right here, and this is our b right here. Okay, so the last question is the middle term twice the product of 2y plus 9z, or is the middle term, okay, twice a and b? So if we multiply 2 times 9, that's 18yz. Okay, and we multiply it by 2, it becomes 36. So the answer is yes. If all three questions, okay, are answered yes, then it simply means that it is a perfect square trinomial. And if you factor that perfect square trinomial, remember the pattern, okay, of a perfect square trinomial. If I have a squared, okay, plus 2ab plus b squared, it is the same as a plus b squared. Okay, so in this case, you have 4y squared plus 36yz plus 81z squared, and we've proven that it is a perfect square trinomial. We can write this as a squared plus 2ab plus b squared. So this is 2y squared plus 2 times y times 9z plus 9z squared, and simply get a and b and put it in this form. So this becomes a, or 2y plus 9z quantity squared. Okay? So let's take a look at the example B. 9n squared plus 4n minus 21. Okay, first arrange the term from descending order. Okay, so let's do descending order. 9n squared plus 49 minus 21, okay, is equal to 9n squared minus 21n plus 49. So let's ask the question, is the first term a square? The answer is yes. Is the last term a perfect square? The answer is also yes, because that's 49. But look where the problem is. Is the middle term twice the first and the last term? The answer is no. So this is not a perfect square trinomial. Okay? Let's take a look at example number 2. Suppose the dimensions of a rectangle can be written as binomials with integral coefficients. Again, integral coefficients mean that the coefficients are integers. So with integral coefficients, if the rectangle with an area of 121x squared minus 198xy plus 81y squared, square millimeters a square, if so, what is the measure of each side of the square? So again, the word problem, so we use a 4-step plan. You know the dimensions of the rectangle can be written as binomials with integral coefficients. The problem gives an area of the rectangle and asks whether it's a square. If it is a square, we need to find the dimensions of each side, or basically we need to factor it. So what do we plan to do? The rectangle is about 121x squared minus 198xy plus 81y squared is a perfect square trinomial. Okay? You must answer 3 questions to determine if it is a perfect square trinomial. If it is a perfect square trinomial, we need to factor it. Okay? So is the first term a perfect square? 121x squared is the same as 11x squared. The answer is yes. Is the third term a perfect square? Yes, it is, because 81 y squared is the same as 9y squared. And is the middle term twice a and b, or twice 11x times 9y? Okay, and the answer to that is also yes, because 11 times 9 is 99 times negative 2 will give you negative 198. So with that done, All we need to do is find A and find B. In this case, our A is, okay, our A is 11x and our B is y. And since this is a subtraction sign right here, we now find our difference of squares to become, okay, 11x minus 9y squared. Okay, so we simply follow the pattern now. Remember what the pattern is. The pattern is if we have a squared minus 2ab plus b squared, which is a perfect square trinomial. You simply get the a and the b, put them in parentheses, and square them. And that's exactly what we did here. Okay, so the measure of each side, okay, is 11x minus 9y millimeters. And if we want to check if our answer makes sense or not, we simply use the FOIL method. And then we find the answer to be to check out. Okay. Now, a question arises, can we use the power of x if it is a perfect square trinomial? Okay. The answer to this question is yes. Okay. We can still use the power of x if it is a perfect square trinomial. Okay. Let me give you a good example of that one. Let's say we want to find x squared. Okay, x squared minus 12x plus 36. Okay, again, ask ourselves, is this a perfect square trinomial? Yes, it is. Is the first term a square? Yes. Is the last term a square? Third term a square? Yes, it is. And is the middle term twice a and b? Yes, it is, because this is 6 squared. Therefore, this should be 2 times 1 times 6, which is the same. And this is x squared, right? So we're the same. This is a perfect square trinomial. Now that means if it's a perfect square trinomial, we can simply get the a, which is 1, and the b, which is 6. And since this is subtraction, let me put that way, this becomes now x, okay? And since this is subtraction, this is x minus 6 squared. That's our a, and that's our b. Our a is x, okay? 12x, sorry, I forgot that x. So this is an x right there. Okay, so how can you use the power of x for this one, or the x method? So again, this is 36, and this is negative 12. And if you notice, the factors of 36, which will give you a sum of negative 12, will be negative 6 and negative 6. And since the coefficient of 1, this is the coefficient of 1, we simply write x minus 6 times x minus 6, or that. Okay, so you can use the power of x for perfect square trinomial, but the pattern will make it a lot easier for you to find the factors of a perfect square trinomial without going through the factoring method of using x. Okay, let's take a look at the next example. As you continue your study of mathematics, you will find that forming a perfect square trinomial can sometimes be a useful tool for solving problems. Let's take a look at example number 3. Example number 3, determine all values for k that make 25x squared plus kx plus 49 a perfect square trinomial. Okay, so again, we want to find values of k which will make this trinomial a perfect square trinomial. So we copy the problem down as what we did, and then we write down 25x squared as 5x parentheses squared and 7 as 49 as 7 squared. Okay, so we get our a and our b. Remember, our a is equal to 5x and our b is equal to 7. So we want to find out which will make this into a perfect square trinomial. We want to do 2ab or negative 2ab. Both of them would make it into a perfect square trinomial. Okay, so in order for this to be a perfect square trinomial, kx must either be 2 times 5x times 7 or negative 2 times 5x plus 7. We just talked about that right there. Okay, or kx is equal to 75. x, okay, because 2 times 5 times 7 is 70x, and negative 2 times 5 times 7 is negative 70x. Okay, and we simply solve for k. Okay, so now we end up with solving for k, divide both sides by x. Okay, you get rid, if you divide both sides by x, you undo x, k equals 70. Okay, and if you divide both sides by x here, you end up with negative 70. So basically, the possible values of k, which will make this a perfect square trinomial, are 70 and negative 70. Okay, so check to see if that is ask yourself the three questions to make sure that 25x squared plus 70x plus 49 is a perfect square trinomial, and 25x minus 70x plus 49 is a perfect square trinomial. Last concept in this lesson would be this. In this chapter, you've learned various methods to factor different types of polynomials. The following chart summarizes these methods that can help you decide when to use a specific method. So first things first, this is your rundown of priorities and when to factor. The first method is to always check for GCF. That's the very first method. So basically, GCF works if you have 2, 3, or 4 or more terms in a polynomial. The second thing, after checking if there's a GCF or not, you need to check for difference of squares. Okay, and in difference of squares, it only works with 2 terms. Okay, and then after that, we do third priority would be perfect square trinomial. Check if it is a perfect square trinomial, because remember, a difference of squares and perfect square trinomials have patterns. You don't have to go through the entire factoring method. Okay, so follow the pattern, you're good to go. Okay, and the fourth step you need to take after checking for GCF, and if there's no GCF or if there is one, check for difference of squares, and then if there's no difference of squares, check for perfect square trinomials. The fourth step would be trinomials that have 2 binomial factors. See, this is now your power of x, or your method x right here. Okay, so that, and pairs of terms that have common monomial factors. So this is basically power of x, and this is the grouping method. So first check for GCF, then check for difference of squares, then check for perfect square trinomials, and then you do the power of x. And then if the coefficient of your quadratic term is greater than 1, so let's say if a x squared, let's say plus bx plus c, and if a is greater than 1, then you use grouping. If a is equal to 1, then no grouping. Okay, so whenever there is a GCF other than 1, always factor it out first, and then check the appropriate factoring methods in order in the table. Okay, use these methods to factor until all of the factors are prime. Let's see how this works. Factor each polynomial. Okay, again, look for the GCF, and we know that 4k minus 100 has a GCF of 4. So we factor out 4, and we end up with k squared minus 25. And then we know that k squared minus 25 is a difference of squares. We factor it out, and there you have it. 4 times k minus 5 times k plus 5. Okay? So the completely factored form is 4 times k minus 5 times k plus 5. Let's take a look at B. 9x squared minus 3x minus 20. Okay? The GCF, okay, is 1, so therefore we cannot factor out our GCF of 1. And this is not a perfect square, since 20 is not a perfect square, and that negative sign, okay, prohibits it. That's not part of our pattern for a perfect square. That's already out, so the trinomial is not a perfect square. So we're left with, okay, the power of x. Okay? So basically, we use the power of x for this one. And we have multiplied 9 times negative 20. 9 times negative 20 will give us negative 180. We want to find the factors of negative 180, which will give us negative 3. Okay? Which will give us negative 3. And in this case, we find negative 15 and 12 to work for this one. So with this, we use grouping. So from there, okay, we rename this to become 9x squared minus 15x plus 12x minus 20. Okay, and we take it from there. We now group them. Okay, so let's group 9x squared minus 15x, okay, plus 12x minus 20. The GCF of 9x squared and 15x is 3x. Factor it out. And the GCF of 12x minus 20 is 4. Again, we factor it out. You now have 3x times 3x minus 5 and 4 times 3x minus 5. Using the distributive property, that's our A, that's our A, and that's our A, that's our B, and this is our C. So we have 3x plus 4 times 3x minus 5. So therefore, completely factored form of this polynomial will be 3x plus 4 times 3x minus 5. So letter C, if you notice, there are 4 terms. So first check for GCF, then check for pairs of terms that have a common factor. So we will check for GCF, then we will start grouping. So the GCF is 2mn, and we factor out 2mn, okay, times quantity 2m cubed plus 3m squared minus 8mn minus 12n, okay, and then we group 2m cubed plus 3m squared, and then plus negative 8mn minus 12n. Okay, we group them. Okay, and then okay, we get the GCF of 2m cubed and 3m squared, and the GCF of negative 8mn and 12n. So we end up with m squared times quantity 2m plus 3 and negative 4n times quantity 2m plus 3. Using the distributive property, we bring down 2mn. This now becomes m squared minus 4n times 2m plus 3. So this is the completely factored form of that particular polynomial. Okay, and the secret word for this lesson would be tiger. Secret word is tiger. And thank you for watching.